Okay, good afternoon, everyone. I believe it is 3 p.m. I know that we have quite a bit to get through, so we will make sure that we use the time that we have available productively. Once again, I want to thank you for making the time to attend today's masterclass with Professor Emeritus Rosemary Falcon. I am Aburengwi Nengovera, and I'm with the Coltech Research Association. For those who may not be familiar with Coltech, we are a research, development, and innovation association that's there to support the coal mining sector. Part of the work that we do, in addition to supporting the sector, is really to make sure that we disseminate important research information to those who are interested and really to those who support the sector. So when we were thinking about these master classes a few months ago, the idea has always been to bring world-class researchers to this platform to contribute their knowledge, their expertise, and insights so that we can all collectively grow in understanding all things that relate to coal, and today specifically things that relate to clean coal technologies. In that world, there are very few people in the world, in my opinion, who can rightfully call themselves experts. And I'm really happy today that Professor Falcon has agreed to really come and share insights with our community. Most people will be familiar with Professor Falcon from the many years she spent at WITS, but also from her time as the previous head of the Clean Coal Research Group, also at WITS University. She has agreed today to take us through just her view of coal in terms of where we are, but maybe more importantly in terms of where, in her view, where this industry is headed. So with that, I am more than delighted, to say excited will be an understatement, to hand over to Professor Rosemary Falcon, who for the next hour will take us through clean coal technologies. We will, in the end, take questions, but if you do have a question during the session, please pop them in the chat box. With that, Professor Falcon, over to you. Thank you.
Thank you very much, Aburengwi. It's a pleasure to be with you and a pleasure to be with good friends. I'm not quite sure who's there, but greetings to one and all. When Abu approached me to make a presentation, which included clean coal, I had a bit of a cheeky thought, and I hope you don't mind. I've called it "There's Black Gold in Them Thar Hills," if it can be used responsibly. So it's a bit of fun. I'm just going to take you through a number of issues that become quite important. Now, as far as this is concerned, just one moment. Why is coal so relevant to South Africa? Why is coal under threat? Why is South African coal unique relative to the US and EU and elsewhere? What is the impact of coal qualities on use? What can improve coal's use image? What could lie ahead? Well, if we start with that at the moment, coal is a critical resource, obviously, in Southern Africa, if one can see this. Oil and gas are fairly plentiful in other areas of our continent. In terms of employment, socioeconomic factors, that is extremely important. If you look at the chain of reaction there, going literally from the primary sector through the secondary sector to the tertiary, plus all the dependent service providers in towns, clinics, and retail, etc., one could average about 700,000 people, which is a lot more than just mining. This becomes quite an important issue. The third most important thing, of course, is its financial value. Highest mining income earner, 90%, that might be dropping down a little bit for the energy production. 75%, or it was until recently, the region's energy source. 100% of our iron and steel alloy reductants, 33% of our liquid fuels, 90% of our cement production, and over 200 major chemicals producing thousands of carbon-based products. The diagram at the bottom will show you the rands and billion terms which coal can offer as opposed to gold, platinum, etc. Why is coal under threat? Well, obviously, the first thing is the greenhouse effect. It's climate change. We've all been told about this. The fact that, in fact, there is a skin on our atmosphere that is projecting or retaining, if you wish, the heat on that skin. The second important thing is that the country is, heavily dependent. The countries are heavily dependent on coal for electricity. And as a result of that, the Paris Accord has brought the world together in a pledge to lower emissions. Of those countries that are the most dependent in coal, you will see at the bottom, Botswana, Kosovo, South Africa is third up. This is very important to us. What can be done about this? Well, obviously, minimize the adverse effects, which are on the left, maximize the economics on the right-hand side. Against the increasing pressures to eliminate the use of coal, there are a number of things that have to be done. First, we need to understand our coal. Secondly, we need to appreciate its true value in all senses, and we have to learn how to use it responsibly. Then why is South African coal unique relative to, for example, the EU and the US and elsewhere? Well, obviously, the one thing for those friends who are geologists will know this. Coal-forming climates and vegetation in the Carboniferous and Permian times will explain this. The top left, between 300 and 350 years ago, the coals of the Northern Hemisphere formed in equatorial conditions. At that time, Southern Africa was undergoing a very intense ice age, as shown in that circle. Not long after that, 250 to 300 million years, the ice sheet had withdrawn. The area around the ice sheet became highly suitable for swamps and coal formation, and the Northern Hemisphere dried up and became hot and unproductive in terms of coal. So in fact, the environments and the climates were extremely different. This is a diagram that shows the extent of that ice age in the Southern Hemisphere of what we would call Gondwana. It is fairly persuasive. During that time, and as it faded, the glaciers that had pushed through the mountainous areas had scraped off sides of the mountains, and that dust, rock dust, had accumulated in the ice. As the ice retreated, as the ice sheet withdrew and the glaciers withdrew, the dust that was found in the glaciers began to be deposited in the swamps when these glaciers melted. This is the source of a lot of the mineral matter in our coals. Not only the glaciers, but the environment in which the coals were forming is important. This is, in fact, the layout in Alaska of exactly what has happened and has been anticipated to be very similar to what was happening in the Witbank-Highveld area, Middelburg, of course, at that time. What you have is valleys around lakes, along seashores and on the river deltas is where the swamps formed. That is where the coal accumulated. But of course, your glaciers melted. We have hot and cold summers and winters, and a lot of flooding would have come down, which brought that clay at times of climate change. One of the other issues, of course, is as these glaciers withdrew, so the plants started colonizing, and plants formed at different stages and different times once this had formed. So what you might find in the plants in your scene number 1 may not necessarily be the same as the plants a little later on. Now, in this particular diagram, you may like to see, it's that vertical period with the pinks and the blues is climate change over the last 500 million years. You will note that, in fact, I'm not sure if you can see my cursor, but what you will note is 4 different ice ages. The blue ice house, the blue is the ice house, pink is the hot house. We have 1, 2, 3, and going vertically to the top, 4 ice ages. We are currently coming out of the Pleistocene ice age. But by far the longest ice age was the one in the middle, the Dwight ice age. That lasted for 80 million years, whilst the northern hemisphere was collecting swamps for coal seams to form. That yellow period that you see above that ice area is in fact the area that the Karoo deposition took place, and the coal seams formed during that time. The line that indicates the drop in temperature towards the hothouse is the change in climates that allowed our coals to form. Now, what happened during that time there is Gondwanaland. You will notice in the middle that there is a little dot with a dotted line. The dot was in fact the South Pole, effectively, around which the ice cap formed, was in the region of approximately Messina, my geophysicists tell me. As the ice receded, the ice cap withdrew, so the actual pole has moved over time into Antarctica. But at that time, as the ice cap withdrew, it changed from what you see in that horizontal bar. The ice sheet, the closing phases, isostatic glacial events, when the actual ground fluctuated vertically a few times as the ice melted and then accumulated again, which allowed for different types of sedimentation. And it is here where the coal seams were formed. As the pole moved even further, climates stabilized and became warmer. Now, this is reflected in the seams that we find typically in the Woodbank area. Number 1 seam and 2 seam are at the bottom. This is a very favorite diagram that was printed many years ago, but it tells such a wonderful story. 1 and 2 are at the bottom, and you see the glacier just behind it. Then you have a very thin 3 seam, and then you have 4 seam above that. As the glacier virtually disappears, and ultimately by the time the 5th seam is formed, there is very little ice in evidence. You'll also note quite correctly that the mountains have become a little eroded and swollen, smoothed up, I should say. Now, this is what you see in the mines. Number 2 seam at the bottom, very thin seam 3, and then the upper 4 seam. Seam 5 is not shown in this particular diagram. Now, during that time, as climates warmed up, floras of the Karoo evolved and changed in response to climate change, evolution, and the environment. Vegetation areas have been, as you will see from the gray areas in the diagram, have actually been defined according to macrofloras, the wood and the leaves, and the microfloras, which are not shown here but have been worked on as well. There are 4 major evolutionary plant series. From the very bottom, which is the Dwight, where in fact you would have had the ice. The seams took place or occurred, number 1 seam at the bottom, number 2 seam, number 3 seam, 4 and 5 as you go up the column of the seams. So this will reflect for you the change, not only in the climate, but in the plants. And obviously in the photograph, in the slide you've just seen, environmental changes as well. This is scene 1. This is the reconstruction of what it was believed to be during the time of the first and the second scene. What you have in the background is the glacier, and this is autumn. We find in the coals a lot of cuticles, leaves that have been deposited during autumn. So we know that the climate changed annually from there. Equally, as the glaciers receded, they deposited their moraines, so the ground was not necessarily flat. It is highly variable. This is reflection of what happened during the time of the fourth scene, number 4 scene. Right in the background, you might have what is the remains of a glacier, but you have uneven ground again, slightly warmer, different plants coming in, wide open, and that is your number 4 seam. The number 4 seam is quite unique in that the lower part is fairly bright and fairly good, or it can be in various areas. As you see, these different waterlogged areas would be areas where your good quality coal would form. The drier areas would be, and above this would be where you would find your less reactive coals. Flooding would still take place on an annual basis. This is reflective of what is happening in Alaska. I was very fortunate, my husband and I, to be in Alaska, and we particularly went there to see what the forms of forests and ground looked like, because what you will see on the right-hand side is certain forests that are bone dry. What you see on the right-hand side has 5 meters of accumulated woody material beneath that surface. That is basically dry coal in the making. On the left-hand side, you'll see what happens in winter. It is covered by snow. Now, it's quite interesting that although there might be a lot of rain there, snow is in fact dry until it melts. So the conditions are very different to what was happening in the equatorial water swamp conditions of the northern hemisphere when their coals were forming. Now, just to give you a little bit of fun, I've added in some plants to prove that we did have plants. What you have in the middle there is a tree trunk, and most notably, you see the annual climatic cycles, the winters and the summers, each one of those basically representing a year. This is fossil wood. What you have on the left is the type of wood where the tree trunks and branches have nodes in them. They were quite unique. On the right-hand side, you actually have the cell structure, which was very advanced at that time and provided the strength for tall trees to form. This is reflection of the leaves at the time. This is the famous Glossopteris flora of the early sediments, not long after the Dwicker had finished. Simple venation with a single midrib. This is the advanced Glossopteris flora, much higher up and much younger. In the later coal seams, probably seam 4, possibly 5. Large leaves with advanced lateral veins. Note the varying forms of the central midrib. Beautiful, beautiful. One could get quite hung up just on playing with plant fossils. Dicruidium flora is the one representing the most advanced flora in the Permo-Triassic period. This is closing on the upper, virtually the boundary of the Triassic at this point. Leaves have become quite advanced, as have the fruits. These are advanced forms of flowers and fruits encountered in the Glossopteris flora. I honestly can't say that they were colored to that extent, but the artist has elected to put them in color. The one on the right is an actual one. You can see very clearly how that has got tiny little, they're not buds, they're actually part of a fruit. You could almost call it a strawberry of about 300 million, 250 million years ago. Moving on, what you see there is an insect wing. I'm sorry, I'm just trying to clear something off my screen. At the top, you have an insect wing, which was found at the close of one of the major ice sheets. And at the bottom right, you have an advanced pollen form. This is a winged coniferous pollen, which is climate adapted. You can see this because that central body where you can see little white striations, that allows that pollen to close up and open only when conditions are conducive for a plant to grow from it. I'm sorry, I'm having trouble here. Just give me one moment. Right, moving on. Composition of the South African coal and its quality. When viewed, this is a photograph I must thank Nikki Wagner, because she brought this from England. I've never had the opportunity to take a photograph as clear as this one. Here you will actually see, and often to hand, bands of dull coal and bright coal, and that becomes extremely important. In terms of seeing it under the microscope, what you have at the top grey smooth area is the bright coal, and the bottom band, microscopically shown, is in fact the dull coal. So that's what you would see if you cut the bright banded coals and looked at them under the microscope. The top one, the smooth grey homogeneous material, is what we call vitrinite. It's grey, smooth, homogeneous, and you will see how it reacts later on. The bottom band is a band of granular material which has been washed in. It's called inertinite, and more specifically inertodetronite. The white is organic material. The grey is in fact clay. Now, there are different forms of dull coals, and that for us in this country is extremely important. The dull coal you see here is actually horizontal layers of woody tissue laid down parallel to bedding. Fusinite is the very strong white with porosity close to the bottom, very strong white band with the original woody cellular structure seen. That is generally considered to be fairly inert, low or no volatiles. The remaining shades of grey are called semi-fusinite. Semi-fusinite being pale grey to dark grey with variable levels of jellification and cell porosity. That material, particularly the upper photograph, is extremely important to us because it does have a proportion of volatiles. It does, in fact, soften on heating, but it is not yet to the level of the vitrinite that you saw in the previous slide. Now, when we calculate the reactivity of a coal, we actually include that top grey material. We do not include the fusinites as a reactive material. Depends on the proportion of grayness. Grayness relates to the proportion of hydrogen in that particular material. Then, of course, you have a different type of dull coal. This dull coal is fine organic detritus washed in during flooding with particles of clay. The black that you see in those photographs is particles of clay. This very fine material washed in would obviously be further away from the actual source of that. It would be sinking in a remote part of a lake or a dam or in your peat swamp. This is called inertodetronite, obviously from the word detrital. The white particles are inert, the grey particles are semi-reactive. This is equivalent, but a much coarser particle range, which obviously has shows the same sedimentation sizes of sandstone when you look at different particles there. This is also a term of inertodetronite. What is important is the white particles are inert, the grey particles are semi-reactive. This is typical. I popped this in just for a bit of fun because it comes from a particular band of coal in the Free State, which is purely an absolute, if I may use the word, hodgepodge of grey clay with very detrital, very inert organic particles of material, which have been dried out or burnt, and they have virtually no volatiles in them at all, but that has been turned coal and sold into one of the power stations. Minerals, the ones on the left shows you different sizes, shapes, and proportions of clay in with detrital particles of coal. Now, how to separate that in a washability is not easy. There are ways of evaluating the potential for that on a microscope. On your right-hand side, you have pyrite. Now, the top two photographs are inherent forms. By saying inherent, it's not chemically bound into a molecule. It's tiny little particles of pyrite, which in fact, your scale, I might tell you, if you see these little vertical lines towards the bottom of the white, that is 550 microns. So those little particles that you see in the second slide are presumably about 10 to 20 microns in size. Those are not easy to wash out. The remaining material, as you go down that column, are particles of pyrite, which according to crushing and types of crushing, you can separate out in a washing plant. The main organic components in coal and how do they react when heated? Particle of vitrinite is well known. The vitrinite particle on the left, fresh coal at 0.1, once heated begins to soften and devolatilize. You see the gas pores in the middle. The sharp edges are rounding off. By the time stage 3 comes, the bubbles have increased in the center. The walls have become thin. It has expanded. And by the time you get to stage 4, that particle is a thin-walled cenosphere or pure char. That is carbon rich. It has lost its volatiles, and that surface, both internal and external, is extremely reactive. Once oxygen links onto the molecular surface, that is consumed in a very quick space of time. On the other hand, inertinite is something different. This particle of inertinite on the left-hand side in coal is part of the detrital band of coaly particles. A lot of this detrital material around that one white item in the middle is relatively unreactive as well. But that particular white one is captured more often than not in the fly ash on the right-hand side. It does not soften. It does not become porous. It might crack a little bit. And the remnants of the remaining particles of inertinite around that particle, you can actually see in the black and white close to the particle on the right-hand side. The fly ash that is embedded in is that material that you see around the particle. This is what I have picked up many, many times when looking at fly ash coming out of Eskom's power stations. So be under no illusion when we say a particle is not reactive. It truly is not reactive. There are a number of different sizes, shapes of particles of char, subject to what is in your coal particles when they go through into the power station. These are pulverized coal. And the time for combustion of these different particles is in fact subject to how easily oxygen can be exposed to that surface, or is exposed to the oxygen, put it that way. The top left-hand corner, all you see there is the remnant of the very tiny, thin end of a cenosphere, almost completely consumed. Why is South Africa considered unique? Many people think that. Well, over many years, we've collected many examples of this. In this case, we're looking at combustion. First of all, you look at your calorific value, similar. Then you look at your proximate analyses, and you'll find in yellow, the ash content in this particular case is 11 to 12. Not often do we find coals with ash contents of 11 to 12. However, the combustion efficiency of coal A is 83%, whereas coal B is only 66%. And when you look at the carbon in ash at the back end of the boilers, the one on left is 4, meaning most of the coal has been combusted. On the right-hand side, 15% is what is left. So 15 to 20% of your coal has gone out of your boiler, thus dropping the efficiency. The reason for that at the time was found to be maceral composition at the bottom. The white 62% is in fact the proportion of vitrinite in that coal. The rank, which is the maturity of the coal, was not considered an issue at that time. So this is an indication of the variation in organic matter, irrespective of your calorific value or your proximate analysis. A second very important example. Some years ago, Germans came out to this country to see if we could sell them blend coking coal for their iron and steel industries. They gave proximate analyses and said, that's what we want, but they didn't work. One of the key issues for coke making is the swelling index, and the swelling index goes from 0 to 9. 9 is the top. Coal A gave 9, coal B with identical proximate analysis. The South African coal had a swelling index of 1.5. The Germans could not understand this. Under examination, of course, the maceral composition vitrinite, which is the source of your most important coke making, was 82%. Now, in this case, equally important was the level of maturity of your coal. This had a reflectance of 1.2. Reflectance being the levels of light coming off the surface of vitrinite as you pass from brown coal, lignite brown coal, through your bituminous range to your anthracite. Somewhere in the middle of the bituminous range, the reflectance value between 1 and 1.6 is where you find prime coking coal. This is 1.2. The coal on the right-hand side has a reflectance of 0.6, which is borderline some bituminous to very immature bituminous, and a 25% vitrinite. That cost industry an enormous amount of money, because where they thought they had a market for their blend coking coal on the basis of proximates, it didn't work. One of the areas that can show very clearly the differences between the coals of Europe and America and South Africa is this diagram. The axis at the bottom is your organic content. On the right-hand side, you have 100% vitrinite. On the left-hand side, 0 vitrinite, 100% inert organic matter. Pardon me. The left-hand axis, the y-axis, is in fact the rank, the degrees of maturity going from lignite through bituminous down to anthracite. Now, in the yellow area on the right-hand side is where the USA European carboniferous coals are found. They are typically highly reactive with vitrinite. They range in rank, but they are well known. They burn easily, quickly, as you saw with that vitrinite particle. South African raw coal varies. Woodbank coal typically is those pink dots going across the upper part in the orange area of this diagram, with two exceptions. On the right-hand side, part of the Waterberg, the upper part of the Waterberg is slightly more vitrinite rich, but also ash rich. And Chikondeni was virtually a prime coking coal, which now is no longer being mined. It's been mined out. The Natal coals are all those in the little yellow blocks that you see. Now, the Free State coals lie on the left-hand side of the Witbank. The general Witbank and Highveld coals lie in the middle of those pink dots. So you can actually see virtually the differences between coal seams, coal fields, coal basins, and continents in one particular diagram on the basis of organic material. Obviously, ash is a big issue for us. We have used up much of the ash categories along the bottom. You'll see 0 to 15% ash at the bottom, even 0 to 20% ash has largely been mined out. And the categories of ash that remain basically are the 20 to 35 up to 65% ash. This is what we are marketing or mining at the moment. And obviously, this has to be dealt with as well. What is the impact of coal qualities on use? Well, in terms of mining and beneficiation, critical, absolutely critical. The seam on the left is typical of the number 2 seam. It could actually be related to the number 4 seam as well. At the bottom, you had the brighter coals, low ash. As you graded up the seam, you had the duller coals and more ash in them. Now, it's subject to what you mine, and different seams and different parts have been mined over time in different ways. Either you take the whole seam out and you wash, as is shown in that diagram, through heavy media separation processes, or you take out selectively and you mine accordingly. In this diagram, we're showing heavy media separation. Now, vitrinite, which is that bright, shiny, very reactive material, has a low density, an average between 1.25 and 1.35. So in your low density fractions, you can actually wash that off. Much of that has gone. What remains now is uneconomic to separate out in many cases. Average, where we were at 1.3, would have an ash content of 8, volatiles around 30, but that is not economic any longer because those parts of the seams or that material has largely been washed out. The middle level is where you capture some of the vitrinite and now most of the inertinite, the dull coal that does not react, or the semi-reactive material. Now, one could blend them together into middlings, or one could discard and then rewash or discard and get more inertinite, which is higher ash. And so basically you can blend a fair amount to actually supply what you need to your customers. However, the proportions of these different washing densities now becomes important, but what is often not considered is what has happened to the reactive material. Where is it? How is it actually going to work? Considering that unreactive material you've just seen, it is terribly important that one knows where that is actually going. Your discard at the bottom can either be made into wonderful products, such as Prof. Samson Bada has done, or be discarded or used for other purposes. Now, because there have been problems and because a lot of our boilers have been designed by overseas people, it is extremely important that one understands in South Africa, and this applies to Southern Africa, we need to design the boilers or gasifiers or whatever else it might be to match our coals. In this particular instant, the boiler was taken from another design from a coal which actually worked very well. They assumed on proximate analysis and CV that this would work. What needed to be done in this case, extreme difficulty in ignition. Mark 7 burner design, it took them 7 burner designs to ignite that coal. 10 meters were added to the height of the boiler because it was so high in inertinite, it just didn't ignite and it didn't burn out. 1 meter extra was added between the burners. Tube mills were selected instead of vertical mills. Burner mouths melted because once you do ignite inertinite, it's like anthracite. It takes a great deal of effort to ignite, but when you do, its temperatures are extremely high. Burner mouths melted. Popcorn fly ash blocked the air heaters because the temperature was so high once the coal was ignited that it melted within the boiler and blocked the air heaters at the back, leaving an unusually high percentage of fly ash. That was a case history that has been of tremendous importance to the actual boiler EOM at the time, but has not necessarily been learnt by people, for example, who designed Medupi and Kusile. A second example of many that we have worked on is flameouts. Because coal goes in and the qualities vary from time to time, you get flameouts. What happens is because this is pulverized coal, it gets pushed into the boiler. It will ultimately, under the conditions of pressure and growing temperature, it will release what volatiles it has, the relatively inert material. The pressure builds up, the boiler explodes. I'm sure we've all heard recently about a number of boilers exploding. The worst explosion was in fact in Hawaii some decade or two back, where an Englishman came out to run the boilers. There was a flame out. He told them to continue putting that in. The boiler exploded and killed 10 people. One needs to understand these coals. Toxic gasifiers. AENCI bought 6 or 10 gasifiers in order to make their ammonia for fertilizers some many years ago. They did not look at the coal. The people designing this brought in a slagging gasifier. Our ash does not slag. Secondly, our coal does not ignite easily. Difficult ignition, long burnout, high carryover, 65% carbon in the fly ash. Difficult heat transfer. Now, the idea for slagging gasifiers is that when you push the coal into the gasifier, the ash, under certain circumstances, will melt and form a lining for that gasifier to protect it from the heat of the organic material now gasifying, except in our case it didn't. So basically, solidification of ash was, it literally glued onto the walls, it didn't melt, and frequent downtime. They had to replace gasifier linings every 6 months. Adaptations to linings eventually helped to some extent. Those gasifiers lasted for 25 years and ultimately were closed down. A fluidized bed boiler was required to burn the 65% of ash coming off the back end. And this is a last case study of an industrial boiler. It happened to be a spread stoker boiler, which one of my students actually managed to get a master's out of. What you have is 4 South African coals, BC grade, 25 to 26 megajoules, ash, 15 to 17, high-grade coal. Different, in this case, because it was a research project, there was a camera put into the boiler. The coal started on the left-hand side and was thrown across to drop down on the right-hand side where the coal, larger lumps of coal remained on, I beg your pardon, remained on the spreading platform, which moved the grate that moved to the left-hand side. So there were two options for coal to burn here. In air, which you see in that top left-hand diagram, ignition in air and ignition on the grate. But ideally, you want the one at the top left. Excellent. The next two diagrams show a little diagram, a little combustion in air, much delay from the right-hand side, and ultimately a little bit of ignition before the coal drops off to the left. In the third diagram, virtually no ignition at all. And in the fourth bottom right diagram, there was an explosion. Now, the temperatures of these coals, the normal one, top left, was about 1500, 1550, which is normal for our coal. These ones further down are 1700, I'll call that 1790, 1721, 1793, almost 1800 degrees. People overseas, when they design boilers with our coal, believe that coals burn between 12 and 1400 degrees, maybe touching 1500 degrees. Our coals burn hot when they burn at all. So as a result of all of that, one obviously has to take into account plant design, operating conditions, and coal quality in order to get compatibility, to find process efficiency, etc., etc. Now, that means the engineering contractors, the coal producers, and the coal users have to talk. What can improve coal's image? Well, obviously, we get back to minimizing what we're all facing, the adverse effects, maximizing the economic benefits. Oh, goodness gracious. Sorry, let me just check something, because I do believe some of my slides have come off. Yes, they have. Let me move straight into this one. Can you actually see this one?
Yes, we can.
All right, then that's better. Now, obviously, one is going to talk here about clean coal technology. It's essential. There are three ways of doing it. One is plant efficiency. That is the nature of the coal coming in, the boiler or gasifier that is being used, plus the efficient process of providing your heat or your steam. Secondly, you have the greenhouse gas pollutants, greenhouse gas being SOx, NOx, and some people include particulate matter there. Those can be captured from processes that are now well known at the back end of a pulverized boiler if necessary. And number three is, what do we do with king problem, CO2? Either store it or use it. And that's really where we're going. There are a number of ways that one can deal with this. Number one is to increase your boiler efficiency. Your vertical axis is, in fact, tons of CO2 per megawatt hour. Your horizontal x-axis is efficiency. The red circle that you see up there is Eskom's current efficiency between 21 and 35. As you go down to the point of 50% efficiency, those little blocks in red, that is the objective for the advanced supercritical or ultra advanced supercritical boilers. 48% is now being achieved globally. That is one of the major issues, is to increase your efficiency. To show that it works, this is a power plant, Samchok, in South Korea, 42.4% efficiency. And at the bottom, you will see the limit value of SOx, NOx, and particulate matter. They have met them without any back-end flue gas desulfurization, etc. It is a clean processing plant, which has been in operation since 2015. Without going through any detail, there are many others, but I selected 4 in Japan, China, Germany, and another one in China. The bottom 2 are now reaching efficiencies of 47.5 and 47.8. These efficiencies are extremely important. The technologies most of them are using is something called circulating fluidized bed, which is the next point that I wanted to bring up. The next step to take in trying not just to be efficient, but to choose the right boiler for the type of coal that you are using. On the left-hand side, you have pulverized coal, which is what we have, which is a once-through of pulverized coal at temperatures up to, in this case, 15 to 1900 degrees C. It's a one-through. You have to mill your coal, high temperatures. You do have melting ash and slagging. It requires NOx because at high temperatures, oxygen bonds with nitrogen in the air. And it requires SOx, which is flue gas desulfurization at the back. Performance is strongly reliant on the quality of the coal going in. So to try and make that efficient with the type of coals that we have is very, very difficult. On the right-hand side, you have the circulating fluidized bed principle, which initially you can see being fed in is limestone coal and biomass. There's a wide flexibility of what can go in. Air comes in the bottom. This operates at 800 to 900 degrees below the temperature at which NOx is made. Coals that cannot burn out quickly and easily are returned to the boiler in a circulating fashion until they are burned out. This allows full 100% use of your carbon. Low temperature retains or means that you do not have any of your melting of your ash. The dry solids keep the furnace clean. Low NOx. SOx is captured in the bed because you are adding limestone within the boiler. You don't need a coal mill. You do not need to dry your fuel. Performance reliability is maintained, but you don't have to worry about that because it has a very wide fuel range. Now, this is the range on the right-hand side, CFB, fuel experience. All that material in that block can be used in circulating fluidized bed alone or with coal. On the left-hand side, PC needs very specific design for a boiler and a limited quality. Right-hand side block gives you the fuel range of experience. Ash contents, CFB can take from 0.1 to 60% ash. It is not an issue. Volatile matter can be highly variable from 5 to 50. Sulfur can be 0 to 8% because you're dealing with it in the boiler. Now, the third issue, so we've gone through efficiency of a boiler, type of boiler. We're now looking at what you actually do with the emissions. And here we know that the emissions that you have in the orange block can be captured by certain processes. One of the processes is being tested at the moment in South Africa by ECPM. That, in fact, can capture particulate matter, SOx, NOx, and CO2, and it makes commercially saleable products. These are the products. Particulate matter has rare earth elements. SOx is now being made and can certainly be made a lot more into sulfuric acid. NOx goes into the making of fertilizer, and CO2 can make other products, which in fact is under review at the moment. And the interesting thing is that if you can capture all of these, plus the remaining ones that are in that orange block, and if it is possible to get your clean air up to 98 100% clean, which the manufacturers are aspiring to do and believe can be done, if not already has been done. What is the problem with using coal? This, I'm very excited to show you, is an example of high value products from CO2. This was a PhD, which became a postdoc of mine, who took Eskom-like coal-fired power station flue gas, the gas that comes off the power stations, and he captured carbon nanotubes. Carbon nanotubes have a $6 billion market. It is possible to do. What lies ahead for coal in South Africa? We know coal is relevant to South Africa. We know why coal is under threat. We know why coal is regarded as unique. We know why. We know the impacts of coal qualities and what they have on use, and we know how to address them. We can improve coal's usage and its image if we use the right technology. We know what could and should lie ahead for coal in South Africa. And these are the two objectives or aims, if you wish, that could be considered. Aim for net zero emissions while still retaining coal in the energy mix. And secondly, take full benefit of the carbon in coal wastes to manufacture valuable products. Let me show you an example. Follow China's lead to reach net zero. China is going to be the first country to reach net zero. China is building dozens of new high emission, high efficiency, low emission coal-fired power stations per year. 165 new power stations were licensed in China in 1 year. China is closing down old power stations or retrofitting them using ultra-supercritical, high-efficiency, low-emissions power generating technology. China's new coal-fired power plants have amongst the highest efficiencies in the world. The results? China's greenhouse gas emissions of SOx and NOx reduced or totally eliminated. China's CO2 emissions have dropped from 500 parts per million to 50. Finally, what can you make from coal as your final aim and objective? Out of coal itself, coal products and discards, all the products that are currently being made by Sasol and others that are being tested and being researched at the moment, millions of dollars are being spent on using coal as the carbon ore. Samson Bardo's particular objective is to get us to do the same thing in this country. We could be earning, as America is, very, very efficiently. When we look at our emissions, the clean air could happen, and the capture from the emissions could provide all of those things as well. So products is there and possible, just not much done at the moment. I conclude with the following wise words from Future Coal's report presented at an event recently. There is a growing divide, which is most interesting, between the northern and southern hemispheres and between the global west and the global east, in other words, the Asian countries, with respect to the use of coal as an energy source. Coal will remain relevant for decades to come in developing countries of the southern hemisphere and the global east, as coal is the cheapest form of energy, the most reliable and the most abundant. Funding must come forth. This is the provision of critical consideration. Funding must come forth to ensure coal's responsible use in those countries, for coal to remain as part of the energy mix. July Ndlovu of Thungela noted recently the long development for wind turbines, for solar panels, and for nuclear to come to the fore. That will be no different to bringing clean coal technologies and carbon capture use and storage technologies to the fore as well. We just need to get there. The Chinese have invested significantly in clean coal technologies and will be the first to reach net zero. We could follow. South Africa has only just begun to install clean coal technology, Medupi and Kusile, with pending flue gas desulfurization. But there are more suitable boiler technologies which are not being installed. CO2 storage may be a way off for South Africa, but there are possibilities in enhanced gas recovery in the gas sector, as we're beginning to find new gas fields both onshore and locally. And CO2 usage is in its infancy. I've shown you the nanotubes that we've produced, but this is being researched globally. South African nanotubes having done that. So there really is life for coal as black gold in them there are hills, subject to, and I leave you to think about that. Thank you.
Prof.
Okay,
Falcon, thank you for that. There are a few moments where one is brave enough to speak for others, but this afternoon I do feel I can speak for all of us on this call when I say we are eternally grateful just for your generosity of spirit in preparing this masterclass and taking us through how you see the future of coal. So thank you for that. I do recognize that it is 4:01, but I do believe, Professor Falcon, that you do have a few minutes. So if there are burning questions, we can take one or two. But for those who may have other engagements, we do understand. Thank you for continuing to support the work that we do, and hopefully you got a lot out of today's conversation. Just checking if we can take one or two burning questions before we adjourn the session. Suppose even general comments are welcome.
I think I talked for too long, Avu.
Well, we do have
confused.
Dr. Mangena, Prof. Beki. Will start with Sitobani.
Great, thank you. Thank you, Chair. Thanks, Rosemary. It's really good to see you and to listen to you again. It's always a pleasure hearing your voice in the coal fraternity. I think all of us share the sentiment.
Thank you.
Good stuff. Thanks. Just a question from me. The boilers we are running, they are coal dependent, and you mentioned that very clearly, to say you design the boiler based on the coal quality. Now we're talking circulating fluidized bed and its versatility. Now, would you say for that kind of a technology, can you just bring it and plonk it here in the country without having to do some test work or demonstration of some sort? Just from a risk point of view, I mean, can you do it like that, or do you need to do some test work?
If I may answer your question, it's lovely to chat to you too. It's a long time since we last met. There is absolutely no doubt about that South African coal. In fact, I took one of my slides out because I thought my talk was going to be, and it was very long. I had 2 PhD students testing our coal, one in America and one the Foster Wheeler pilot scale test plant in Finland. South African coals were tested in both conditions. The one in VTT, which is the Finnish one, we tested a very reactive, good quality Russian coal. We tested a very high grade, clean, very good steam coal from South Africa. We tested a middlings and we tested a discard. And do you know, every single one of them had 98 to 100% efficiency, without any shadow of doubt. The only slight variation was that the discard didn't ignite within the first fraction, but it picked up because of the inert material within it. The highly reactive coal initially flared up and then slowly catered off until that was completely burnt out. You could actually see the combustibility of the different products. All coals burnt to 98 to 100% efficiency. The coals that were tested in America showed that some of our coals, and there was a number of coals, 4 or 5 coals had been taken over there. Those coals actually showed that many of our coals have got calcium in them. And the calcium in the coal, in the minerals in the coal, actually reduced the sulfur. If it was a high sulfur discard coal, the actual SOx coming out the back end was negligible. It had been captured in the boiler with the discard. I mean, there are so many important factors that we're just not getting out there in the places that need to be got, because we have coals that would work remarkably well with all of this. Does that answer your question?
Yes, let's say 70%. Maybe a follow-up quickly, if I may, Avrengu. So from a research point of view, or from an RDI point of view, do you think there's a need for us as a country to look at the CFB from an RDI point of view, or do you think we can just bring the technology and implement?
There is absolutely no doubt whatsoever that we do need a research center here to give it some test work. On that score, if I might just explain, in about 2018, I think it was, some colleagues and I put together a program. I'm sure that Northwest University, and that you were part of there, we had Northwest, we had University of Natal, we had Wits University, we had Mintech, Eskom, and Sasol were part of a group that put a 100-page proposal through to DSI for a research center working around a reasonably sized, it has to be reasonably sized, it cannot be laboratory sized, a reasonably sized circulating fluidized bed boiler that all could research in and could develop for testing our coals for different reasons. That proposal was going to be funded very heavily by Eskom, some by Sasol, some by DSI, and we were hoping NRF would come to the party, and they had agreed, if the project went through, that they would fund that as well. It went up to 3 or 4 different levels of government assessment with other projects for that year. We were the last 2 projects to be considered, and the other one got the funding. It went to hydrogen. So in fact, that project is still available, and it is critical that we do something like that. My only beseeching is that it shouldn't be locked in. Eskom wanted to have it on their premises, but the condition would be that only Eskom would be controlling it and using it and testing it. We said, no, you need to have a group of people who would manage it generally, but different universities or different OEMs, in other words, boiler manufacturing people, might like to have test work done, and you would have a control team looking after it, or you would have research projects done by various students at various universities. You've got to have collaboration on this. It cannot be a one-off. That is my only concern. Zeribani, I think it's important that we go back to this, because it's not only us. I came back from Botswana a week ago. They are looking at the potential of not just exporting their coal, for obviously internationally if they can get the railway line done, but maybe developing their own power generating center to supply for the rest of Africa and supply us if we run out of power. And obviously their coal is similar to ours and will have the same problems. So the chances of being able to use a research center, not just for us, but for the countries in the Southern African region is enormously important. Does that answer your question?
Yes, thank you very much. Maybe let me just put it to the colleagues on the line. I work for the CSIR now, and we have an opportunity. The CSIR being a national research institute, housing something like this is something we can do. So yes, thank you for that.
That's a pleasure.
Thank you. I think we'll take the last question from Prof. Bekir so that we can release the attendees. Prof, if you're ready, you can ask or comment.
Thank you, Abu. And I just wanted to thank Prof for taking her time and enlighten everyone within Caltech community. And it's good to know that there is so much more potential for the future of coal. And, we're still going to be around to see coal succeeding forward. Thank you, Rosemary. Really appreciate it.
Bekir, that's so kind of you. Thank you. I appreciate your words. It's a long battle. It's a long, hard battle. But if we have enough people that feel convinced, if enough work has been done to prove what can be achieved, we'll get there. We'll get there. I hope.
Oh, Falcon, for as long as I've been aware of coal, I have been aware of the work that you have done and the work that you continue to do. So again, on behalf of all of us, thank you for making the time and all the prep work that went into this. We really, truly appreciate it. And to all the attendees, thank you for continuing to support. And let's continue to build this community together. For more information, you can always visit caltech.co.za. With that, we'll adjourn the session. Thank you very much.
Thank you, Abu. Goodbye to you.
Cheers.
Bye.